Welcome back, everyone. We're diving into a topic today that sounds like something straight out of science fiction.
Oh, yeah.
It really does.
Okay.
It's action at a distance in quantum mechanics.
Oh, wow.
I know, right?
Yeah, that's a good one.
So, you hear that and you're like, wait, what? What does that even mean?
Yeah.
So basically, it's the idea that a change in one system can instantly affect another system no matter how far apart they are. Almost like there's nothing connecting them.
Yeah, it's kind of like, if you had two coins and you flipped them on opposite sides of the universe,
Wow.
they always landed on the same side.
Yeah.
That's how counterintuitive this is.
Yeah.
Because in our everyday world, we're used to things influencing each other through direct contact.
Right.
Or forces that travel through space like light or sound.
Exactly. If you reach out and touch something,
Yeah.
or you hear a sound wave.
Yeah.
But it seems like in the quantum world, there's a whole different set of rules.
Uh-huh.
And to kind of wrap our heads around this, we're going to be looking at the Stanford Encyclopedia of Philosophy's entry on action at a distance in quantum mechanics.
Okay, cool.
So yeah, get ready, because this is going to be a wild ride.
So to really understand this, we need to start with one of the most famous thought experiments in physics,
Okay.
the Einstein-Podolsky-Rosen.
The EPR.
Yeah, EPRB experiment.
Okay.
Or EPRB for short.
Okay.
It was later confirmed by real-world experiments.
Oh, wow.
And it really just kind of shook things up.
Okay, so walk me through this EPRB experiment.
Sure.
What's the basic setup,
Okay.
and why was it such a big deal?
So imagine a source that emits pairs of particles.
Okay.
Now, these aren't just any particles.
Okay.
They're linked in this really special way, so their properties are correlated.
Mhm.
Like you think about those two coins slipping to the same side.
Right.
Even if these particles fly off in opposite directions and end up light years apart. Measuring a property of one particle, like its spin, seems to instantly determine the state of the other particle.
So you're saying that by measuring one,
Yeah.
you're automatically determining the other one, even if they're light years apart.
It's like there's this invisible thread connecting them
Oh, wow.
across vast distances.
But wait, doesn't that completely contradict Einstein's theory of special relativity?
Uh-huh.
The one that says nothing can travel faster than light.
Exactly. That's the problem that the EPRB experiment presents.
Okay.
It seems to suggest that there's some kind of spooky action at a distance
Right?
where information or influence is traveling instantaneously
Yeah.
and defying the cosmic speed limit.
So is it possible that the particles were just pre-programmed to behave this way? Maybe they were both set to spin
Yeah.
in a particular direction from the start?
That's a natural assumption to make.
Yeah.
And it's what a lot of physicists thought initially.
Okay.
But then it came along John Bell. Oh, I've heard of him.
And his groundbreaking theorem,
Yeah.
which completely changed the game.
Okay, so let's talk about Bell's theorem.
Okay.
How does it explain what's going on with these spooky particles?
So Bell's theorem is this mathematical proof that basically says that the results of the EPRB experiment
Okay.
cannot be explained by any theory where influences are limited to the speed of light. It throws a wrench in any attempt to explain the particle's behavior using what are called hidden variables.
Oh, so those pre-programmed instructions you were talking about?
Yeah.
Okay, so what's the big takeaway here? Does Bell's theorem definitively say that action at a distance is real?
The essential insight from Bell's theorem is that the quantum world must be non-local.
Non-local.
Meaning that influences can act instantaneously across any distance.
So it's not really action at a distance in the traditional sense?
Right.
So what are we actually seeing with these entangled particles?
Okay.
How do physicists make sense of this? Well, some physicists argue that what we perceive as action at a distance in the EPRB experiment might actually be a manifestation of holism or non-separability.
Holism.
Yeah.
Okay, those sound kind of philosophical.
Yeah.
What do they actually mean in quantum mechanics?
So holism in this context means that the whole system, those two linked particles, has properties that can't be explained just by looking at the individual particles themselves.
Yeah.
It's like a jigsaw puzzle.
Okay.
You can't understand the complete picture just by looking at the individual pieces.
Right.
They only make sense when they're all connected.
So it's not that one particle is magically influencing the other.
Right.
It's that they're part of a single system even when they're separated.
Exactly.
Okay. And what about non-separability?
Non-separability reinforces that idea, suggesting that these linked particles are fundamentally entangled and can't be treated as independent entities no matter how far apart they are.
So they're like two sides of the same coin, even when that coin is somehow split across the universe.
Yeah.
This is seriously making me rethink everything I thought I knew about reality.
Yeah.
But if all of this is true, how do the different interpretations of quantum mechanics try to explain what's going on?
Yeah.
Do they all agree on this spooky action business?
Well, that's the fascinating thing about quantum mechanics.
Yeah.
It challenges our very notions of reality.
Yeah.
And to answer your question, no, not all interpretations of quantum mechanics agree on how to handle this spooky action at a distance. There's no single universally accepted answer.
Okay.
Each interpretation has its own way of grappling with this puzzle.
Okay. So let's dive into these different interpretations.
Yeah.
What are some of the leading contenders in the quantum mechanics arena?
One of the most well-known is called orthodox quantum mechanics.
Okay.
Sometimes referred to as the Copenhagen interpretation.
Got it.
This interpretation suggests that when we measure one of the entangled particles, it causes the other particle to instantaneously collapse into a definite state.
Okay.
Even if they're light years apart.
So it's like the act of measurement forces the other particle to choose a side.
Yeah, you could think of it that way.
But how can a measurement have such a profound effect on a distant particle?
Right. Those are some of the conceptual problems with this interpretation. It works mathematically, but applying it to the real world, especially at like larger scales, gets really tricky.
Okay.
That's why other interpretations have emerged to try to address these problems.
So what are some of these other interpretations?
Okay.
Do they all involve spooky action at a distance?
Let's start with collapse theories, like the GRW and Pearl models.
Okay.
These try to make the collapse process more concrete, less of a mysterious, instantaneous event.
Okay.
They propose that particles randomly localize in space at specific moments, leading to the collapse of entangled states.
So instead of a measurement magically affecting the other particle,
it's
more like a spontaneous localization event that happens to both particles at the same time.
Exactly.
Okay.
It removes some of that spookiness by introducing a more physical mechanism for the collapse.
I like that. A little less spooky.
Right.
Okay, so what else?
Then we have Bohm's theory, which takes a completely different approach.
Okay.
It introduces a guiding field.
A guiding field.
That permeates all of space and influences the motion of particles.
Okay.
This guiding field is responsible for the correlations we see in the EPRB experiment.
So, like, there's this invisible hand guiding the particles' destinies.
Yeah, you could think about it that way.
Okay.
Making sure that their properties are correlated.
Yep.
Even when they're far apart.
But wouldn't this guiding field also need to transmit information faster than light? To maintain those correlations?
That's a valid point, and it's one of the reasons why Bohm's theory is considered non-relativistic. So it's a fascinating theory that provides an alternative explanation for the EPRB correlations.
Right.
But reconciling it with Einstein's relativity remains a challenge.
It seems like we keep coming back to this tension between quantum mechanics and relativity.
Yeah, they don't always see eye to eye.
What are some other interpretations?
Okay. We also have what are called modal interpretations.
Modal interpretation.
Yeah. They propose that quantum systems have definite properties, even when they're in superposition states.
And that's when a system exists in multiple states at once, right?
Exactly. These interpretations try to address the measurement problem without invoking collapse.
Oh, so no spooky action at a distance or sudden collapses?
Not in these interpretations.
Okay.
It's more about uncovering those pre-existing properties that were always there, just hidden within the superposition.
So they were always there, we just couldn't see them.
In a sense, yes.
Okay.
So what else?
And then, of course, we have the most mind-boggling of them all. Oh boy, I'm ready.
The Everett-like interpretations.
Okay.
With the famous many worlds interpretation being the most well-known.
Oh, yeah. Many worlds.
Okay. These interpretations propose that all possible measurement outcomes actually occur, but in different branches of reality.
Whoa. So every time we make a measurement, the universe splits,
Yeah, that's the basic idea.
creating parallel realities where each outcome plays out.
It's a pretty wild concept.
It is what?
And in this interpretation, the EPRB correlations arise not from spooky action at a distance,
Okay.
but from the branching structure of the universe itself.
Hmm.
So the entangled particles are correlated because they share a common history before the universe branched.
So instead of instantaneous communication,
Right.
it's more like two particles taking different paths in a multiverse.
Exactly. It's a radically different way of thinking about reality.
It really is.
And it continues to spark debate among physicists and philosophers.
Okay, so we have all these different interpretations.
Yeah.
Each with its own way of explaining this action at a distance thing.
Right?
Can we actually use this spooky action for something? Like, could we send messages faster than light?
That's the million-dollar question.
Right.
The idea of superluminal signaling,
Superluminal signaling.
transmitting information faster than light,
Yeah.
is incredibly tantalizing.
It would completely change everything.
It would upend our understanding of the universe.
Imagine sending a message to a distant star system and getting a reply right away.
Right. It would transform space exploration, communication,
Everything.
our understanding of time itself.
So is it possible?
Here's the catch.
Okay.
Most quantum theories suggest that superluminal signaling is impossible,
Oh, man.
even the ones that embrace action at a distance.
So even with all this quantum weirdness, we're still stuck with the speed of light as the limit.
It seems so.
Okay, but what about this whole non-locality thing and Einstein's theory of special relativity?
Yeah.
How do those two fit together?
That's a question that's puzzled physicists for decades.
Yeah.
Can quantum non-locality and special relativity coexist,
Right.
or are they fundamentally incompatible?
Okay.
The answer is surprisingly complex,
I figured.
and it's still being debated today.
I bet.
So some physicists argue that the apparent superluminal influences that we see in quantum mechanics challenge the spirit of special relativity.
Okay.
They say it violates a core principle of relativity,
Okay.
that nothing can influence events outside its light cone, which is the region of space-time that can be causally connected to a particular event.
So for them, quantum mechanics and relativity just don't mix.
Right. They see them as fundamentally at odds.
Okay.
But other physicists argue that special relativity only forbids superluminal signaling,
Okay.
not all types of superluminal influences.
So there's a difference between sending information faster than light
Yeah.
and having correlations that appear to be superluminal. So maybe there are other types of influences that operate outside our understanding of spacetime.
It's possible.
Okay.
And some physicists even suggest that these superluminal influences might point to a deeper, more nuanced understanding of spacetime than we currently have.
So our current framework might need to be expanded
Yeah.
to accommodate both quantum mechanics and relativity.
That's one way to look at it.
But before we get too deep into that,
Yeah.
what about those local quantum theories you mentioned earlier?
Okay.
Are there any theories that try to explain all of this without non-locality?
There are some physicists exploring those possibilities, trying to develop these so-called local quantum theories
Okay.
to find loopholes or alternative explanations that preserve locality.
So they're trying to make quantum mechanics fit with our classical intuitions,
Well, you could say that.
like having our cake and eating it too, but without any spooky consequences.
Yeah, that's a great analogy.
Some of these approaches involve questioning the validity of Bell's theorem's assumptions,
Right.
while others try to exploit the inefficiencies of real-world measurement devices.
Exactly.
So they're looking for cracks in the foundation,
In a sense, yes.
hoping to find a way to maintain locality without contradicting the evidence.
That's the idea.
But so far, these local theories haven't been as successful as the non-local ones.
That's right.
So for now, it seems like action at a distance,
Yeah.
or at least some form of non-locality,
Yeah.
remains the best explanation for these quantum correlations.
That's the current consensus.
Okay.
But the story is far from over.
Right.
New discoveries could always shift the paradigm,
Yeah.
leading to breakthroughs, or even entirely new ways of understanding the universe.
Exactly. Wow. And it seems like the more we learn about quantum mechanics,
Yeah.
the more questions we have.
It's a never-ending journey of discovery.
It really is.
Yeah.
But even without, definitive answers,
Yeah,
it's incredible to think about all the implications.
absolutely.
So let's recap what we've learned in this deep dive into action at a distance. Okay, we started by exploring the mind-boggling concept of influences seemingly traveling faster than light.
Right, those superluminal influences that seem to defy our classical understanding of the universe.
And then we delved into the EPRB experiment,
Yeah.
which showed those impossible correlations between entangled particles.
And how those correlations just couldn't be explained by any kind of pre-existing instructions or hidden variables.
Right, and then Bell's theorem came along and just threw a wrench into everything.
Yeah, it really forced us to confront the possibility of a non-local universe where influences can act instantaneously across any distance.
Then we went through a whole bunch of interpretations of quantum mechanics.
Right, each one offering a different perspective on how to make sense of this spooky action at a distance.
From collapsing wave functions to guiding fields and even branching universes.
It's amazing how diverse and mind-bending these interpretations can be.
And while we talked about the possibility of sending messages faster than light.
That superluminal signaling idea.
Right, it seems like most theories suggest it's probably not going to happen.
Yeah, the speed of light still seems to be the ultimate speed limit.
And then we even touched on that big quote of how quantum non-locality fits with Einstein's special relativity.
Yeah, those two seem to be in constant tension. Like they're speaking different languages.
And while some physicists are trying to find ways to explain these quantum mysteries without invoking non-locality at all.
Yeah, those local theories.
They haven't been as successful so far.
So it looks like, for now, action at a distance, or at least some form of non-locality, remains the best explanation we have for these quantum correlations.
That's the current state of play, but who knows what the future holds?
Exactly. There could always be new discoveries and breakthroughs that completely change our understanding.
That's the beauty of science. It's a constantly evolving journey.
It really is. And even though this deep dive might have left us with more questions than answers, that's okay.
It's all part of the process.
It's about embracing the mystery and continuing to explore. Absolutely. And not being afraid to question what we think we know.
So as we wrap up this deep dive, I just want to leave everyone with one final thought.
Okay.
Don't let the complexity of these ideas intimidate you.
Right.
Let them spark your curiosity and fuel your desire to learn more.
Keep asking questions. Keep digging deeper.
Exactly. Keep those brains buzzing.
Universe is full of mysteries waiting to be uncovered.
Absolutely. And until next time, keep exploring the amazing world of science.